Okay, so in this video, we are going over 7.5, which is scale drawing and dilations. Again, we've seen scale drawing and dilations earlier when we did our transformations unit, but they are also an example of similar figures, so that's why we touch base on them here as well. So again, some of this might look familiar, and if not, then just act like you've never seen it before. But again, we did do dilations in the transformations unit. So the objective is I can interpret dilations and use scale factors to solve problems. And the first thing I want to go over, just, again, is some vocabulary. There is a lot of vocabulary in this unit. You'll remember I made you guys do that Desmos activity the other day, and I realized there is a lot of vocab that you guys are still struggling with. So luckily I already have built in this little vocab review. But let's talk about this and then we'll continue on. So first off, it says dilation. That is a transformation that reduces or enlarges the original figure proportionally. A dilation changes a figure's size, but not its shape. Since a dilation produces a similar figure, a dilation is a type of similarity transformation. So again, that is why it was also part of our transformations unit, because it is an example of one. But it's similar, not congruence. The center of dilation. Dilations are performed with respect to a fixed point called the center of dilation. This is often the origin. At least in this class, you can dilate from other points, but oftentimes the origin is where we're dilating from. Pre-image. The pre-image is the figure before the dilation. The other way that we've been referring to this, kind of the colloquial way of referring to that, is the old figure where you started, the pre-image. And then again, the image is the figure after the dilation. And then scale factor. The scale factor, K, is the ratio of the image compared to the pre-image. So again, it's always new over old. If I'm going too fast, please pause the video to catch up. And then an enlargement is a dilation with a scale factor that's greater than 1. So K will be bigger than 1, like times 2, times 3, times 4.5, whatever. Where the image is larger than the pre-image, versus a reduction. That is a dilation with a scale factor. And it's not greater than 1, but it's also not negative. It is between 0 and 1. And the best way to think about that is your fractions. If you're half as tall, you're going to be shorter. If you're 2/3 the size of something, it's smaller than the original thing. So that's where that's coming from. But if it's negative, that doesn't really make sense. Okay, so we talked about a perimeter of similar polygons. I don't actually think that's the right title for this, so if you want to cross that out, I think I borrowed that box. But basically, this is just kind of continuing to go over scale factor. So if K is greater than 1, it's an enlargement. If K is between 0 and 1, it's a dilation, the dilation's a reduction. Scale factor, again, is always going to be image over pre-image. Or again, that new over old. And so if I have this diagram over here, the first one is about triangle FGH, where FGH is the pre-image, so this is the old one, and then the green figure is the new one. And what we want to do on here is we just want to write out the proportional sides. So if I go through and match up the sides that go together, the proportion would be TS over HG equals RS over FG equals RT over FH. More of the same. We're just matching up the corresponding sides. They would all have the same ratio because they're proportional. And then on that second one, ABC is the pre-image or the old one, and then the little green one is the new one. So again, we can match up those sides as well. New over old, new over old. So let's see. It would be AB. Oh, sorry, wait. New over old. WX over AB equals YX over CB equals ZY over DC equals ZW over DA. So again, just really keeping in mind what is the new and the old figure, writing out an extended ratio with all of those proportions. Same stuff we've been doing up to this point, honestly. But the main time we see dilations is with word problems and then also on a coordinate. You've seen this a little bit, but again, dilations oftentimes we're doing on the coordinate plane. So there are some examples. It says determine whether the dilation from figure A to figure B is an enlargement or a reduction. Then find the scale factor of the dilations. Okay, so the first thing I'm going to do is label old and new. If you remember, it's going to tell you, and if it doesn't tell you, then the assumption is the one on the left is the old one. But in this one, we're told, so I have A as the old figure, B as the new figure, and then on this one, I have A as the old figure, B as the new figure. I really do label those on my own so that you don't have to go back and check anything and kind of remind yourself it's just written there. Then for the K value, we need to do new over old. And essentially, you just need any two sides that go together. So if I'm looking at these two triangles, I don't really know the diagonals. You can't really count them. But what I could do is use the bases. So on the blue triangle, and let me make it blue so it matches, the base is 1, 2, 3, 4 units. Then on the green triangle, I can find that entire distance. Again, it has to be the full distance, including those 4 blue units. So 1, 2, 3, 4, 5, 6, 7, 8. Now I have 2 corresponding sides. So then you can go through, again, do new over old. So the new figure is the bigger one. The old figure is the smaller one. We can reduce that to 2 over 1. So that's my scale factor. And then you can say if it's an enlargement or a reduction. You also could have said that ahead of time, but this is an enlargement because it got bigger. The benefit of number 2 is those are rectangles, so it's a little bit easier to count the sides. I think what I'm going to do is I'm going to count the height of each, though, because it looks like I have like a half unit if I were to count the width. So the height of the green figure is 2. The height of the blue figure is 4. Again, new over old, so the little one over the bigger one because the new one's green. I can reduce that to 1/2, and then again, we need the word, which is a reduction because the original figure got smaller. So really, I don't think that's anything new compared to what we've been working on, but again, just really connecting this to dilations and making sure that you realize it's the same stuff. Okay, let's take a look at this one. The large picture has a width of 2.5 inches and the smaller one has a width of 0.5 inches. Okay, so let's write those in. Again, if you're given information, I go ahead and, note it. So the big figure is 2.5. The small figure has a width of 0.5. If the smaller picture is a reduction, what is the scale factor? So here's the thing, it is kind of hard to tell based off the diagram which one's old, which one's new, but we are told that the smaller picture is a reduction. So that means that is the new one and we started out with the larger figure. Oops, sorry, old. Okay, so if it was a reduction, we need to find the K value. The K value should be between 0 and 1. So we can do new over old, 0.5 over 2.5. I don't really like that as a decimal, so we can convert that to a fraction and have your calculator do it, but it would be 1 over 5, which is the scale factor. Again, that does make sense for a reduction. So that picture is 5 times as small as the original. These are the type of questions we did in Unit 2 for transformations. So it says, find the image of each polygon with the given vertices after a dilation centered at the origin with the given scale factor. Write the coordinates of the image. So this is something that you actually might have forgotten a little bit. So what you want to do on these questions is we have to start out with actually this part, the original figure graphing it. So we need to be good graphers. If you are not a confident grapher, well, sorry, but work on it. So I have 0, 6, and then I have -6, -3. It's kind of tricky because -6 is technically like 1 unit off the graph, but you can still put it on the graph and get a good idea, and then we are going to be reducing it, so it's not going to get any farther off the graph. And then S is at 6, -3, so here. That's just a nice little triangle. And then what we're told to do is we need to dilate that by a scale factor of 1/3. So if you remember, the way that we find the new points on this is we're going to have them be prime. And you take the scale factor and it gets multiplied by all of the x's and all the y's. And I can write that in. Some of us can probably do that in our head for this example. Others can put that in the calculator. But essentially what you're going to do is you're going to say, okay, what's 0 times 1/3? 0. What's 6 times 1/3? 2. And then you keep going. What's -6 times 1/3? -2. What's -3 times 1/3? -1. What's 6 times 1/3? 2. What's -3 times 1/3? -1. And then we can graph those as our prime points. So 0, 2 is Q prime. -2, -1 is R prime. +2, -1 is S prime. And then again, these have the exact same shape, or they should if you did it correctly, so you can kind of visually tell that yes, that does look like a reduction. Yes, it does look like that reduction happened by a scale factor of 1/3. Okay, then we're going to do the same thing on the next one. So again, I'm going to start out with the given points. We are doing an enlargement on this one because k is equal to 2, so it's greater than 1. So I have 2, 1 as my a value here, 0, 3 as my r, -1, 2 as s, and d is 0, 1. Okay, so here's my original points. Again, connect it, try to keep these neat. Sometimes I get very, very lazy diagrams on here, so make sure they look nice. Then I'm going to go through, again, we're going to find all of the new points, which are going to be our prime points. So A prime, R prime, S prime, D prime. And I get that by taking my scale factor and multiplying each and every x and y value to get my new points. So I would have 4, 2, 0, 6, -2, 4, 0, 2. Then I can go through, graph those, make sure they end up in the right spot with the correct labels. And connect. If you want a ruler for these, you can go get one from the front of the classroom by where I normally sit there in the shoe organizer. You also can always use like a debit card, school ID, things like that. But again, make sure it's neatly dilated, and then you also know what points you had after the dilation and you label them with prime values, because again, that gives us a really good indication where the old and the new figures are as well. For anybody that is going into things that are kind of artsy, even along the line of like architecture, engineering, but also graphic design and stuff, you will be doing a lot of scale drawings and modelings and things like that. So that's going to be the last topic, because scale drawings and models are another example of dilations. So it says a scale drawing or scale model is an object or drawing with the lengths proportional to the objects it represents. The scale factor of a model or drawing is the ratio of a length on the model or drawing to the actual length of the object being modeled or drawn. So this is actually one of those things in math that you do see all the time. Even every time you see something on the television, obviously it is a scaled version of what you would be seeing in real life. Maps are a really, really great example on why we care about scales being accurate and consistent and how we can, model something like the ground, the earth, the planet, with a scale to help us understand, where things are located. So the first example, it says the scale on the map shown is 0.4 inches or 0.4 of an inch equals 40 miles. Find the actual distance from Nashville to Memphis. The distance between Nashville and Memphis, on the map at least, is 1.5 inches. Okay? So the general idea on this is we are trying to convert from inches to miles. And oftentimes on a map, the ratio is given as that, a ratio. So 0.4 of an inch to 40 miles. Don't forget, though, we can also have that be a fraction because ratios are just a different way of formatting fractions. And so what I'm going to do is I'm just going to label, there's not really like new and old on this one necessarily, but we do have inches and miles. And I know that 0.4 of an inch is equivalent to 40 miles. So those two things are related. Again, on the, I guess that would be new over old, right? So like the map was made as a model of a real distance. So the map would be newer. So the inches would be new versus the miles, which would be old. And again, we have 0.4 of an inch representing 40 miles every time. So all we need to do is say, okay, well then what does 1.5 inches represent? Because the ratios should be the same for everything. So the ratio of the scale on the map is going to be equal to the ratio of the actual distance. So on the map, it's 1.5 inches. We need to figure out the actual distance, in real life. But it's still new over old in a way. You can also think about it as just organized by units. Now let me organize this a little bit better. So we need to cross multiply to solve. So I get 0.4x equals 40 times 1.5. So 0.4x equals 60. And then we would divide both sides by 0.4. So x is going to equal 150 miles. The other way you could think about this, if you had this problem on a Kansas assessment or ACT or something, since it's 0.4 and 40, that 0.1 inches is 10 miles because that's dividing them both by 4. And then you could multiply that by 15 to get up to 150 as well. So that's also just kind of a way of checking it. Okay. Next, it says Prairie Village is 550 miles from Nashville, Tennessee. Using the same scale, how many inches would Prairie Village be from Nashville, Tennessee on the map? Okay, so this is another example. Again, we have that scale. Now we know the actual distance, but we want to find the distance that we would have on the map. So again, I can use that scale. But instead of knowing inches and finding miles, we know miles and are finding inches. So we need to have 550 on the bottom where the miles are, again, that old distance, and we need to solve for the new distance, which is inches. So in this case, I would have 0.4 times 550 equals 40x. 0.4 times 550 is 220 equals 40x, and then I can divide both sides by 40. So x equals 5.5 inches. Again, if you remember, like I said, 0.1 inch is 10 miles, so 5.5 inches is 550. Okay, last but not least, it says, this is a miniature replica of a 1923 checker cab. The length of the model is 6.5 inches. The actual length of the car was 13 feet. Okay, so again, this is the model, so this is going to be the new one, and this model is 6.5 inches long. The original car, or the old, was 13 feet. Okay, so that's what we're starting with. Then it says, what is the scale of the model? So again, we just have to relate two sides, new over old. It's okay if they're different units because like up here, we had different units on the top and the bottom, so that happens. So I would start by saying, okay, 6.5 inches over 13 feet. And then we need the scale, so we can reduce it to 1/2, but you still have to have the unit. So the 1 inch goes with 2 feet as the scale. So anything that was an inch on the model was 2 feet on the actual vehicle. Then it says how many times as long as the actual car is the model. This is a situation where you do need to compare units. And the reason why is because if we're trying to figure out how many times as long, you cannot say, oh, well, the car is 6.5, or the model is 6.5, the original is 13, so it's twice as big, which doesn't make any sense, right? Because we know full well that a teeny little model, if you multiply it by 2, you do get 13, but you get 13 inches, not feet, which is how the car is being modeled. So our option basically is to say, okay, well, do I want to convert the length of the big car to inches, or do I want to convert the length of the small car to feet? And what I think I would do is probably figure out the length of the large car. So the old car, the original car, we know is 13 feet. But what we can do is we can figure what that is in inches. So 13 times 12 gives me 156 inches. So basically what happened was the car that was 6.5 inches was multiplied by something to get 156 inches, and we can solve for that something by dividing both sides by 6.5. So x equals 156 divided by 6.5, which would be 24. So the big car is 24 times as big as the small car. And that's it for the notes. So make sure you have finished up 7.5. This would be a good time if you missed any other notes to go get caught up on them. And then you guys can work on your assignment. I hope you're being good for the sub, and I will see you guys later.